Hello everyone, welcome to my presentation. Today I'll be talking about how to turn construction checklists into a machine-readable format. But before we get into the technical stuff, I first want to plea my use case that we sort of tackle in this research. So if you imagine a construction inspector being doing his job, he's basically juggling three different kinds of worlds. He needs to keep up with the schedule, he needs to know the plan, the building model, whatever the format is, and then he also has to have his domain knowledge, how to inspect stuff, what are the inspection requirements that are applicable in his country or even in his research, in his niche. And we found that there's a lot of high-value legacy data, especially in terms of construction checklists. Those are checklists that the inspector uses to inspect whatever he's expecting next, and those are still in paper PDF format, and those can't be linked to a schedule or can't be linked to a BIM model, for example. So if you want to think of building an agent or even a robot that in the future will conduct those inspections, that legacy data is basically lost. So one more important thing is that those checklists are basically very, very large. Sometimes for construction components, more than 10 requirements that needs to be checked. So they are very large. There are thousands of items, and translating them by hand would be a tedious task and is not feasible. So we came up with an LLM pipeline where we take in the natural checklists and we use LLM and basically grammar to translate them into existing standards and ontologies. In this case, we are using the IFC standards, so it can be linked to a BIM model. We're using the AEC3PO to map to specific requirements, and we also needed to extend the ontologies by our domain-specific extension that we to fill in basically the gaps that we have found. So how did we start? We first looked at how the checklists are structured and what we can take away from it. And first thing that we've noticed is obviously they are made for humans. So they are made for humans. They are made in a way that a human can perform them efficiently, but a machine would probably struggle with it. So if you have a checklist and there's an item like this bathroom renovation example, check if the mirror, paper holder and towel rack is properly installed. A machine would struggle if one of those is missing, but a human would basically write a note next to it, all but one. That happened a lot of times where objects were bundled 60% of the time in the sample that we analyzed. And that was one of the main issues that we found. Another thing is that basically construction inspections follow simple grammar rules. So an instruction always consists of a verb, an object, and then a modifier. And basically built on that, we built an output that we thought would fit an inspection. We called it the inspection triad. And we basically broke down an inspection task that needs to have one object, and that's mapped to an IFC class. Then we have an action that's mapped to either the AE3PO or our domain specific extensions. And then we have a criteria that's basically something that needs to be checked. It can be, if it's a tolerance, if it's given in millimeters, that would be a criteria. Yeah, so we built an architecture around it to translate those legacy documents with LLM, using LLM into basically a database that can later then be used, hopefully for agents and robots to do the inspection for us. But since this is quite messy, I'm going to highlight a few key features here. We first take in our legacy data. This is via PDF or whatever format it comes in. Then we try to split them down. using a Python script. We identify with the library the object of a sentence, and if we detect multiple objects in a sentence, we try to break it down into separate tasks. So for example, the example I showed earlier would be, we have three different, we split those in three different tasks, one for paper holder, one for towel rack, and one for mirror. And that way we called it atomization because we sort of split the bundle tasks into smaller tasks. Then we used the RAG. We didn't fine-tune any LLMs. We used the RAG. We converted basically all the ontologies, every class of in the IFC class into each individual vector. And we found that the IFC class is so huge compared to all the other ones. We had a drowning out effect that is basically only we're recommending IFC classes or injecting IFC classes. So we did a split that only 50% of it can be IFC classes. That makes sure that we also have representation in our prompt from from the other existing standards. Then we basically asked the LLM to map it. In the prompt, we had examples of how to map it, and we also asked the LLM to also provide a translation, meaning if something would be translated to, for example, IFC wall, we asked it to identify the word that was translated, and that this translation we used later to verify if that's in the original input, and we had sort of a validation loop through that to catch any hallucination. And then here again, then we basically had a loop that if something, I mean, we had rejects, but we had him reason again, and through that we had a greater accuracy. So what are our results? We took the tedious time and took 200 inspection instructions and annotated them by hand and translated them into a machine-readable formats, and then we compared it to two baselines that we thought would fit. One zero-shot line. Basically, we asked Gemini to do a zero-shot blind, basically use IFC classes, and gave an example, and it was bad. Then we did a zero-shot with context. We pasted the IFC classes with it to create our output, and our pipeline at the end performed the best. So to conclude my presentation, again, we took legacy data, we built a hybrid pipeline, and we found a way to represent inspection tasks through something called the inspection triad, and we are hoping to use in the future into autonomous inspections or BIM agents to use that information that has been locked up in legacy documents for so long. That's it. Thank you very much.